Hi. For today's work, what I want you to do is remember what happened in the normal distribution. We talked about the normal distribution. We know what it looks like. We know what standard deviations are and how the curve fits. And 70%, 95%, 99% of the area under the curve. Sort of recall that. In fact, I'll show you a picture to help you recall it. The distribution of the average x bar is normal. It's centered at mean. Its standard deviation we'll call sigma sub x bar. If you can see that, that's a sigma, which is this symbol for standard deviation, and x bar here to show you that I'm talking about the standard error. So this is really the standard error or the standard deviation of x bar. And if we take the mean plus the mean minus 1, we get about 70% of the area. That's where the inflection point is. If we took the mean minus 2, the mean plus 2, this distance from here to here would contain 95% of the area, and the distance between here and here would contain 99% of the area. Well, what is that area? What is that area? What does it mean? Well, it means if lots of people went out and got data, and made x bars out of their data, and came to us, and we plotted their x bars, 70% of them would have their x bars somewhere in this interval. 95% of them would have their x bars somewhere in that interval. And 99% would have somewhere in that interval. This is the 70%, this is the 95, and that's the 99. Okay, that's the idea, is that the area represents observations, represents x bars, possible values of x bar. So if you were to send billions and zillions and quadrillions of people out to measure the size of a book, say, and they came back with their x bars, and we plotted them, and they started filling up the screen, one on top of the other, 70% of that data would be in here. 95% of that data would be in here. 99% of that data would be within that range. Very little would be outside that range. Okay? Well, if the value of x bar, let's talk about this interval here. Let me draw it and make a big mark here. This range here, let's say for argument's sake this was 5 and 10, just to give two numbers, 5 and 10. And that means the true mean is what? 7.5? Okay, 7.5. And the range here is from 5 units to 10 units. This says 70%, approximately 70% of all the people that go out and take data and bring me data will have numbers between 5 and 10. That's what it means. But it means something else. It means that they will be within one standard deviation from the mean, from the true mean. When someone comes in with an observation, right, here's their observation. They come on here. There's a 70% chance that they're in this interval. Let's put them here. They are within one standard deviation of the mean. How often will people be within one standard deviation of the mean? 70% of the time. How often will people be within two standard deviations of the mean? Well, they will be within two standard deviations of the mean 95% of the time. How often will they be within three standard deviations of the mean? They will be within three standard deviations of the mean 99% of the time. All right? So, they will differ from their mean by less than one standard deviation 70% of the time. They will differ from the mean by less than two standard deviations 95% of the time, and they will differ from the mean by three standard deviations or less 99% of the time. Well, having said that and drawn the nice picture, what I want to do is I want to redraw the picture from another perspective. Here, I tell an artist, I say, draw me a picture, and here's what I want. I want x bar to be no more than one standard deviation from the mean 70% of the time. And I want x bar to be no more than two standard deviations from the mean 95% of the time. And I want x bar to be no more than three standard deviations from the mean 99% of the time. Draw me a picture. Well, he could draw the picture we just drew because that's where we got that information. But he might draw the following picture. He might put x bar in the center and say, okay, I'll draw a picture here. one standard deviation from x bar contains 70% of the area. And the area has to do with mu. So 70% of the time, mu will be within one standard deviation of x bar. 70% of the time, mu will be in one standard deviation of x bar. This is mu. Within 95% of the time, mu will be within 2 standard deviations of x bar. And 99% of the time, mu will be within 3 standard deviations of x bar. That's the same thing he was told, only he drew the picture differently. Instead of putting mu in the center, he put x bar in the center. This picture is easier for someone to interpret, although statistically it is not correct. And the reason why this is not correct is because mu is not a random variable. Mu does not vary. Mu is fixed. Mu really is the fixed quantity, and the variable, the thing that changes, is x bar. But conceptually, the distances doesn't make any difference whether we talk about different mu's or different x bars. Let me sort of, this is a difficult concept. If you're fuzzy right now, don't worry. It's not surprising. This is extremely difficult. But once you got it, once it comes through, you will have it forever. So relax, try. We go out and we measure an x bar. And we say, well, there's a 70% chance that my x bar is within 1 standard deviation of the mean, true mean. There's a 70% chance that my x bar is within 70% of the mean. That's easy to understand because there's a 70% chance we're in that area which is within 1 standard deviation of the mean. Right now, that's all I want you to keep in mind. That statement, that I've gone out and gotten x bar, and it's a variable, I don't know where it is, but there's a 70% chance that it's in this interval. Okay. If that's the case, and there's a 70% chance that the mean is within 1 standard deviation of x bar, I say that I am 70% confident, and this is the wording we use, and we try not to use chance or probability in this because because mu is not a random variable and it looks like we're making it one, but we know what we mean. We said I am 70% sure, there's 70% chance that x bar is within 1 standard deviation of the mean. Well, then it's a 70% chance that the mean is within 1 standard deviation of x bar. But in order not to be deceiving anybody, I write it this way. I am 70% confident that the mean is within 1 standard deviation of x bar. Or if you're using the regular data, the mean is within 1 standard deviation of x the mean is with 1 sigma over the square root of n of x bar if you use the regular standard deviation. If you use the standard error, then it's within 1 standard error of x bar. Okay? And similarly, 95 is 2 standard deviations, so I'm 95% confident. Because there's a 95% chance that my x bar will be within 2 standard errors of the mean, so then I am 95% confident that the mean is within 2 standard errors of the x bar. I'm just saying it backwards, but they mean the same thing. They're within a certain distance of each other. And for 99%, I am 99% confident that the mean is within 3 standard deviations, standard errors. See, if you're going to say standard deviation, be careful. There's a difference between this standard deviation and this. If you say standard deviation, you should say standard deviation of the square root of n's. But the standard error, within 3 standard errors. And we will frequently say within 3 standard deviations, realizing that, hey, we're talking about a distribution, and this is the standard deviation of the distribution we're talking about, and it happens to be x bar. So people will use standard deviation rather than standard error. Beware. Beware. Be careful what standard deviation you're using. Keep in mind that if you actually use standard deviation of the data, this is the formula, not this. This is for standard error. Okay? Straightforward, nothing to it. Well, really is nothing to it. Let's do an example. Let's say I have data. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, that's silly data, but let's say that's the data I got. So there's my data. There are 9 observations. N is 9. X bar, which is my estimate of mu, is 45 divided by 9, or 5. My estimate of sigma, that's the estimate of sigma for the data, is the sum of x. Take each of these values, subtract 5 from them, and square them, and divide by n minus 1. 9 minus 1 is 8. I get 2.74. So my estimate of sigma is 2.74. Now, the estimate of the standard error is 2.74 divided by the square root of 9, or 1/3 of this, which is 0.91. So this is my standard error. This is my mean. And now I can sketch a picture, if I want, for the distribution of the x bar. Or I can go straight to my confidence intervals. I can say, I am 70% confident that the true mean, which I don't know, is somewhere between x bar and 1 standard error, or 5 plus or minus 0.91. If I want to write it out, I say the mean is somewhere between 4.09 and 5.91. That is 5 minus 0.91 and 5 plus 0.91. I am 95% confident. I'm 70%, sorry, 70% confident that the mean is in here. I also say sure. Sometimes people use the word sure. I am 70% sure. That means there's a 70% chance that x bar is within 1 standard deviation of the true mean. The way we write it is that the mean seems to be varying, but it's not. It just, there's a 70% chance, or I am 70% confident, 70% sure that the mean was within 1 standard error, that the mean is within 1 standard error of the average, 1 standard error. That gives me an interval called a confidence interval. This is a 70% confidence interval for the mean. Now, I'm 95% confident that the mean is within 2 standard errors, 2 standard deviations of the average, which is 5 plus or minus 2 of these, which 2 9-1s is 1.82. And if I add and subtract, I am 95% confident, 95% sure that the true mean is somewhere between 3.18 and 6.82. I don't know where, but I'm confident it's in that range. This is a 95% confidence interval for the mean. 99% confident that the mean is within 3 standard errors of the average. 5 plus or minus 2.73, 3 of these. If I add and subtract, I am 99% confident that the mean is somewhere between 2.27 and 7.73. Those are called confidence intervals. Okay, what do we learn? That we can say something about those parameters that we don't know the value of. Only up in heaven do they know it. We can give confidence about ranges. If we only want to be a little confident, we give a small interval, plus or minus 1 standard deviation. 70% confident. It's not too confident. You want to be more confident, you have to sort of increase the size of the range. Well, it's in this. The book is somewhere between 8 and 10 inches. I'm 95% sure of that. You have to change the size of your interval. Now, the interval will change as the confidence goes higher. You want more confidence, you have to give a bigger spread for your mean. How can you decrease this spread? How can you make it smaller? Get a smaller standard error. Smaller standard error means small. If you want to be 95% confident, it's the mean, it's the x bar, the average, plus or minus 2 standard errors. And the only way you can change the size of that interval is to change the size of your standard error. Well, you can make the standard error smaller by taking more observations. So someone says, that's too big an interval. You say, well, are you willing to pay for me to take more observations? If you do, I can make the interval smaller. You want the interval half the size? I have to take 4 times as many observations. You want it 1/10 the size? I have to take 100 times as many observations. But can be done. So you increase the confidence, increases the size of the confidence interval, increase the number of observations, decreases the size of the confidence interval. Okay? Remember confidence intervals. We'll be using it in other lectures. Okay? See you.